This is TWiT.
The Juno spacecraft is out there, it's orbiting Jupiter, and we are now getting data back. I know John gets so excited about this. We all do. We love space science.
You know, there's 3 Lego figurines on the Juno probe. There's one of Jupiter, one of his wife, and one of Galileo.
That's hysterical.
And they have a deal with Lego where they put little Lego figurines on all these space probes.
That's awesome.
Quite what the aliens, when they find these, are going to think is, you know.
They're going to think we were very primitive when we sent little icons of ourselves. We did talk about this back on episode 60, but let's get an update. Rob Ebert is on the line. He's a research scientist with Southwest Research Institute. Rob, great to talk to you.
Hey guys, how you doing?
So the principal investigator for this comes from Southwest Research Institute, and you work in conjunction with NASA, right?
That's correct.
Okay. So where are we right now? Where is Juno?
Juno is on an outbound leg of its 6th orbit, moving away from the planet, probably 20 to 30 planetary radii from Jupiter.
Okay.
Oh, that's quite far out. It's not going to come any closer, or how close is it going to come?
It comes, the closest it comes, which we call it perigove, is 3,000 to 4,000 kilometers from Jupiter's cloud tops.
Wow. And
that's when Juno is at its closest period to Jupiter, and it basically does a pole-to-pole pass in about 2 hours. Oh, but the orbit itself takes it well beyond the planet. About 110 Jovian radii from the planet is the furthest it reaches in its orbit.
So it's quite an elliptical orbit. Why is that?
That was actually initially by design. Mm-hmm. When they designed the mission, they wanted to have time to operate all the instrumentation prior to getting into the shorter orbits that were planned for Juno. And so they designed, initially it was 106-day orbit, and then it got broken down into 2 53-day orbits. But how things worked out, we're actually in 53-day orbits for the rest of the mission.
I was going to say, because there's a problem with the main engines, as I understand it.
Let's just say that when you have a spacecraft in orbit that's taking great data, you don't want to put it at risk.
Yes, absolutely.
And Jupiter is very volatile. You've got storms at both poles, right?
Correct.
And is there a big magnetic field as well as it gets closer?
Jupiter has the largest magnetic field in the solar system, and we've measured it as close to the planet as any spacecraft has ever done. And the magnetic field strength at closest approach was about 10 times that of the surface field strength here at Earth.
So that could complicate the mission significantly as well.
There definitely has to be design implementations to deal with that.
Yeah.
Got it. And I gather the magnetic field is quite different than we thought it would be. I mean, it seems to be fairly uneven in places, and you have a very odd effect with your auroras there that the spacecraft actually got some good images of.
Absolutely. So there's a number of things actually to talk about regards to that statement. The first is that the magnetic field was much stronger than we predicted, and the predictions were based on models that were developed using magnetic field observations from previous missions to Jupiter. But the difference is that the spacecraft that explored the planet previously didn't get as close. And so there's some components of the magnetic field that basically decrease very rapidly with distance from the source, from the planet. And so you need to get very close to the planet to measure those. And with Juno, we were able to do that. Also, there was a lot of spatial variability in the magnetic field that was unexpected. And that's leading some interpretation that maybe the dynamo that produces the field is actually closer to, say, the surface, or the surface at Jupiter is really the cloud tops. It's closer to that than we previously thought. But again, this is still early days, so we have a lot of data to analyze and collect before we can come to a definitive conclusion.
And no signs of a black monolith anywhere, you know?
Well, that's right. How 2001 starts is on Jupiter, isn't it?
It's right. We're looking, but not yet.
So what have we learned? What kind of thing? I mean, there are obviously already some surprises. What are we learning?
We've learned a lot.
I bet.
So Juno is focused on a number of main themes. One is, what's the origin and evolution of Jupiter? And then what is basically exploring the polar magnetosphere and aurora? And in terms of the origin and evolution, we're measuring Jupiter's gravitational field to high precision, magnetic field, and peering through the cloud tops deep into the atmosphere. And this is something that really we haven't done on a global sense, the only time that we've been able to take measurements below Jupiter's cloud tops was during the Galileo era, when we actually sent the spacecraft into the atmosphere as at the end of the mission.
Crash landed it, yeah.
So, but what we're learning now is, so this image here, we've never explored Jupiter's poles. Wow. And this is the first, I think this is from Perijove 1. This is the first time, actually, no, let me take that back. This is a compilation of several passes. But this is the first images ever of Jupiter's southern pole. And it's just, first of all, just looking at the imagery is striking. It almost looks like an oil painting, or
beautiful, yeah,
a Van Gogh painting. You know?
But are those all storms? These whorls?
So a number of the things that you're looking at there are cyclones.
Cyclones.
Wow. Yeah. So these are storms.
The side of the planet.
Yeah.
These are storms that are rotating. This is the southern hemisphere, so they'd be clockwise rotating storms around low pressure regions, and they're tending to cluster around the pole. But there's a lot of other structure there too, embedded within there as well. A lot of features that we're really just now starting to try to understand.
Has the image been colorized, or is that the actual color?
No, I think there's some synthetic colorization.
Yeah.
I'm not a imaging processing person, but I don't think these are true color.
Yeah.
Well, good news. If you are an image processing person, you can actually, I understand, get access to the raw photos from the camera.
Absolutely. So all of these images are on a website, www.mission, you've already got it up, missionjuno.swri.edu. From there, so basically the visible camera called Juno Cam is not only a scientific tool, but it's also being used as in a public outreach effort to try to engage the public in this mission. And there's several ways you can do that. One, if you're taking images of Jupiter yourself, you can upload those onto the website, and they're actually using those to create mosaics of Jupiter prior to each pole-to-pole pass. The second way you can do that is you can actually vote on where you want the Juno image to focus during these polar passes. So you can basically help JunoCam select what regions of Jupiter's atmosphere they're going to measure. And then finally, you can get the raw images and do image processing yourself. Nice. And a lot of the images that have been released have had actually processing done by what we're called, citizen scientists or amateur astronomers, and are getting credit and doing great work.
So that's interesting. This is more than a publicity stunt. There are actually a lot of amateur astronomers out there who have the skills and the abilities to add to the work you're doing?
Correct.
Wow.
Yeah, and when they find the stuff, it's...
Look at these images.
It's just amazing.
It is like art. I mean, it is...
Yeah, it's incredible.
That could be H.R. Geiger.
Yeah, and when you think
incredible.
that the entire funding for NASA to make this happen is about a couple of cents per person in the US. I mean, it's
well worth it.
Oh, and we're learning so much from this.
So do you have another 50? How many more orbits do you have? Another 53-day orbits cycle?
Oh, so we're on orbit number 6. We are going to go to orbit 33.
Okay.
So we're going to be orbiting Jupiter for the next 4 years.
Lots more images to come.
I was going to say, is it something that could be extended, or is the probe expected to sort of start to degrade after that time?
Well, so one of the issues with flying a spacecraft in Jupiter's environment is that it has the most intense radiation belts in the solar system. And so with the orbit that we have, we are flying through that region. Now the orbit's designed to try to minimize that, but as we progress through the mission, it gets worse and worse. And so there's a possibility that our instrumentation starts to degrade due to radiation damage. But another way of mitigating that is a lot of the electronics are housed in a vault, basically a shield for the electronics. So so far so good. Everything looks to be operating well, and there's no real sign of degradation. But the original mission was planned to be 1.5 to 2 years. Now we're talking about 5 years in that system. So it's difficult to say what the spacecraft will be like at that time.
Then again, when it comes to building things to last, NASA is possibly the masters of this. The Opportunity probe is still trundling across the Martian surface 11 years later, and it was only predicted to last for 3 months.
Juno's almost 6 years old. It did a really interesting kind of slingshot around the Earth to get out to Jupiter. I thought that was really a cool maneuver. And tell me about JADE. This is an auroral experiment you're doing. Why are the auroras so interesting?
Well, many different reasons. One, so the aurora produced at Jupiter are the strongest observed in our solar system, and you know, we've done a lot of work of understanding the auroral processes here at Earth, but we don't really understand the processes that produce them elsewhere. You know, this sort of the picture's the same, but the details we're not sure if they're different or not. You know, one difference, say, between Earth and Jupiter is that at Earth, the processes that lead to the production of the aurora are externally driven. What that means is that there are structures that are basically released from the sun, and if they can interact with the Earth's magnetosphere, which is sort of the magnetic bubble around the Earth, and the process of basically the process that interaction leads to produces the aurora. At Jupiter, the aurora is produced by processes internal to the system. And so we want to understand how those processes work. And by understanding how that process works at Jupiter, we can understand how that process works at other planets, both in our solar system and the number of exoplanets that we're observing around other planetary systems. So it's just a way of us trying to better understand the physics of one aspect of these environments, and then trying to put that into context of what we already understand.
Just remember, though, you're not allowed to land on Europa, right? That planet, keep away. I've heard that they keep away from, attempt no landing on Europa. I'm just saying.
All the other planets in the solar system are yours.
Yes.
Hey,
we don't have any plans for that.
This is not science fiction. This is science fact, and it is truly awesome.
So what happens at the end of Juno's mission?
Well, if we do the deorbit plan, we'll basically just deorbit into the atmosphere, similar, I guess, to Galileo. I'm assuming the instruments will be on, and we'll collect data until we no longer have communication.
Fantastic.
Well, look at that. Wow.